Welcome to the June 2025 Further Maths paper 1. This is Further Pure 1, FP1. All right, question number 1 is about Simpson's rule. Thomas Simpson was an English mathematician from the 1700s. What makes him interesting is that he didn't come from a traditional academic background at all. He was born in 1710 in Leicestershire, and his father was in fact a weaver. So mathematics wasn't something he grew up surrounded by in the way that we might imagine for some of the other famous mathematicians. In fact, he taught himself. He was largely self-taught. He spent years teaching himself while working, and through sheer persistence he became so good that he began giving lectures and writing textbooks. Eventually he became one of the most respected mathematicians in Britain and even became a Fellow of the Royal Society, which is an extraordinary rise when you think where he started from. The method we call Simpson's rule, which I'm using here, is the numerical integration technique we use to estimate the area under a curve. We do this by fitting parabolas or quadratics rather than straight lines like the trapezium rule does, so you get a more accurate answer. Anyway, for part A, plugging 2 in, we get 3.35 out. Then Simpson's rule gives us an estimation of 4.8. To adapt the integral, what we can do is use the identity cot squared x will be equal to cosec squared subtract 1. So if we want to approximate e to the cot squared x, we can replace that with e to the cosec squared subtract 1, which I'm going to split up into e to the cosec squared x, which is the integral we've already calculated, over e to the 1. Now e to the 1 is a constant, so I can take 1 over e, or 1 over e to the 1, or e to the minus 1 if you prefer, out the front of the integral. And it's 1 over e lots of the calculation we have already carried out. So we can take our 4.8 from part B and just divide it by e. That comes out as 1.8. And that's my answer for 1C. Question 2 is the Taylor series. To do the Taylor series, which is continuing the theme of modeling complex functions as polynomials by looking at the derivative at different points. Named after Brooke Taylor. Brooke Taylor was born into a wealthy, well-educated family in Middlesex, so quite unlike Thomas Simpson. He came from a much more privileged background, privately educated, before going to St. John's College, Cambridge, where he studied law formally, but increasingly focused on mathematics. He became a Fellow of the Royal Society in 1712, and then later its secretary. So he was regarded very, very highly as one of the best British mathematicians of the time. All right, question A, all I'm doing is taking the initial differential equation and I'm differentiating it implicitly. So d cubed y by dx squared plus 3 lots of d squared y over dx squared. To differentiate the 2xy, I use the product rule, minus 2y minus 2x dy by dx equals 0. And then I'm going to differentiate it again. Just carrying out each differential one at a time. Eventually we get the expression equal to 0, and I move all the parts that are not d4y by dx to the 4 to the right hand side, and we get the equation that they wanted. That should say d4y over dx to the 4, not dx to the 2. I've spotted the mistake, so please do not write in. It does not count this time. For part B, essentially we're just evaluating the different differentials at this point when x equals 2 and y equals 1 to construct our Taylor series polynomial. f of 2 is equal to 1, tells us that in the question. Similarly, f dash of 2 is equal to 1, also given in the question. To find second differential, second derivative, I'm going to go back to the original differential equation and plug the numbers in. So d2y by dx squared will be equal to 3 lots of dy by dx, that's 1. Subtract 2 times the x-coordinate is 2, the y-coordinate is 1. It's going to be equal to 4. From that we can deduce that d2y by dx squared is equal to 5. So f double dash of 2 is equal to 5. Using the first version in part A, the first differential, we now have expressions for d2y by dx squared and dy by dx and x and y, so we can plug them all in and then move it over to the right hand side. We get the third differential is -9. So f third differential at 2 is -9. And lastly, the fourth differential, where we can use the final answer for our part A, plug the numbers in there. We're going to get d4y by dx to the 4 will be equal to 4 lots of dy by dx, 4 lots of 1, plus 2 lots of the x-coordinate times by d2y by dx squared, so 2 lots of 2 times 5, subtract 3 lots of -9, and that's going to be equal to 51. So the fourth differential is 51, and that allows us to write our Taylor series. So y equals 1 plus x minus 2 plus 5 over 2 lots of x minus 2 squared. I'm just plugging it into the formula now. Plus 3 over 2 lots of x minus 2 cubed plus 17/8 of x minus 2 to the power of 4. That's my polynomial that represents a solution at that point. All right, that's question 2 done. Question number 3, we've got an inequality to solve. Just looking at it, I think I can split this up into 2 sections. X can't be equal to 5 because we'll be divided by 0, so I'm going to split it up into x being greater than 5 and x being less than 5. When x is greater than 5, it allows me to multiply both sides by x minus 5 without having to consider sign changes, because it's going to be positive. And expanding the right hand side out, we're just left with a quadratic inequality we can go on to solve here. I've brought it all onto the right hand side. Common factor of 3. And that factorizes quite nicely. So 0 is greater than x minus 6, x plus 2. So normally I would extract out, therefore, the solutions, x being between -2 and 6, but because initially I said that x had to be greater than or equal to 5, that just gives me the range of values of x between 5 and 6. For when x is less than 5, essentially the denominator will start off as negative, but then will become positive because of the modulus symbol there. So I can write that as 5 subtract x. Essentially I've multiplied the denominator by -1, ignoring the modulus. That 5 minus x is going to be positive, and therefore I can multiply both sides by 5 minus x. And we're left with a different quadratic. Expand out the right hand side. I can multiply by that 5 minus x because I know it's positive without having to think about swapping the sign around. I've brought everything onto the left hand side this time. Nice to have a positive coefficient of x squared if you can. And this factorizes quite nicely as well. Fine if you use the formula, it's not a problem. 5x minus 22 and x plus 2 is greater than 0. Therefore, x is going to be less than minus 2 or greater than 22 over 5. However, 22 over 5 is just a little bit over 4, so I can have numbers bigger than 4.4, but I've dictated that it must be less than 5, so I'm going to cap that one off. Then, so between 22 over 5 and 5. So full solution then, we've got x is less than negative 2, x is between 22/5 and 5, or x is between 5 and 6, the union of those for question 3. Question 4 is leading us towards the Maclaurin series expansion. The Maclaurin series is just the Taylor series with the courage to start at 0. Maclaurin himself was born in, that's Colin Maclaurin, born in 1698 and died in 1746. He was a Scottish mathematician born in Argyll. Somewhat of a prodigy, he entered the University of Glasgow at just 11 years old, graduated in his mid-teens, and then became a professor of mathematics at the age of 19, making him one of the youngest professors in history. Isaac Newton, you may have heard of him, recommended that Maclaurin be given a position at the University of Edinburgh, where he spent most of his career defending and developing Newton's methods of calculus. So let's construct the tools we need for Maclaurin here. We've differentiated using the chain rule, and then differentiated using the chain rule again, combined with the product rule to get the second derivative. To start tidying this up, I'm going to factorize out an e to the 2x. So we get e to the 2x, two lots of 15 plus e to the 2x to the power of a negative half. Subtract e to the 2x, lots of 15 plus e to the 2x to the power of negative 3 over 2. And then close the brackets at the end. Okay, I'm going to rewrite both of those parts inside the outside brackets, if that makes sense, as fractions. I'm going to try and write them with a common denominator. So taking the 2 lots of 15 e to the 2x to the minus a half, I can write that as 2 lots of 15 plus e to the 2x all over 15 plus e to the 2x to the power of minus 3 over 2. If you think about the powers, it's like saying 1 subtract 3 over 2, and the powers would give us the minus a half. And then that allows me to just rewrite the second part with the common denominator, quite straightforward, e to the 2x over 15 plus e to the 2x to the power of 3 over 2 as well. So we can now expand and subtract the numerators. So we'll get 30 plus 2 lots of e to the 2x minus e to the 2x. I'm going to simplify that straight away as e to the 2x over the common denominator. And now I'm going to put the e to the 2x back into the numerator. So e to the 2x, lots of e to the 2x plus 30 all over the 15 plus e to the 2x to the power of 3 over 2. Which is what the question wanted. Okay, so for B, we have all the tools we need to construct the Maclaurin series. We know that when x is 0, y is going to be 4. then we can calculate the first derivative when x is 0, and then the second derivative when x is 0, remembering to divide by the appropriate factorials in the Maclaurin series expansion. Anyway, you end up with 4 plus a quarter of x plus 31 over 128x squared. For c, we know sine x, the first two terms are x subtract x cubed over 3 factorial. Therefore, if we want the series expansion for sine of 3x, I'm just going to replace the x with 3x in that expansion, so x becomes 3x, and then we'll get 3x cubed over 3 factorial, which simplifies down to 9 over 2x cubed for part C. So 3x minus 9 over 2x cubed. For part D, we can now calculate the limit as x tends to 0 of this particular fraction. The subtract 4 after the root 15 plus e to the 2x. The subtract 4 bit allows me to remove the 4 from the expansion for my answer in B, and that's all over the expansion for part C. And then divide the top and bottom by x. We'll get a quarter plus 31 128ths of x in the numerator, and 3 subtract 9 over 2x squared in the denominator. Well, as x tends to 0, the parts involving x are going to disappear, leaving us with a quarter over 3. And therefore, my answer for part D is 1/12. There we go. Question number 5. So this is using the incredibly sneaky Weierstrass substitution, or the half angle tangent substitution. It allows us to write tricky looking integrals with sines, cosines, etc. As sort of nicer functions, rational functions in terms of t. Weierstrass, Karl Weierstrass, German mathematician, considered the father of modern analysis. His path wasn't particularly straightforward. His father wanted him to study finance and administration at university. He initially went to do a sort of a civil service economics degree, but instead of attending that properly, he became far more interested in mathematics, fencing, and student life. He actually spent years teaching in secondary schools as a largely unknown quantity, before finally publishing some papers that were so strong that the universities realized how exceptional he was and snapped him up. So you never know where I might be in a few years' time. Happened to Weierstrass. Anyway, we know that if t equals tan x over 2, cosec is going to be 1 plus t squared over 2t, and dx will be equal to 2 over 1 plus t squared dt. Those are given when we use the Weierstrass substitution. So our integral, instead of cosec, we'll have 1 plus t squared over 2t in there, and we'll times it by 2 over 1 plus t squared dt. And this question just becomes a challenge of rearranging that the product of those two fractions in a sensible way. First thing I'm going to do, multiply the top and the bottom by 2t. It gets rid of the fraction in the left hand fraction, denominator of that fraction. So we're left with 4t at the top, 2t plus 1 plus t squared on the left denominator, and 1 plus t squared on the right. So times those two together in brackets. And all I'm going to do is factorize the 2t plus 1 plus t squared. That's going to be 1 plus t all squared times by 1 plus t squared. The squared inside the bracket, which is what the question wanted. Okay, so now we have a rational function in terms of t. we stand a much better chance of integrating. We're going to do this using partial fractions. So 40 over 1 plus t squared times by 1 plus t squared, but differently. I'm going to split those up into 3 separate fractions. I'm going to have an a over 1 plus t. I'm going to have a b over 1 plus t squared. And then I'm going to need a ct plus d over the 1 plus t squared one. So I can't split that 1 plus t squared up in a different way. All right, multiplying through by the denominator, cancelling where appropriate. 40 is equal to a lots of 1 plus t plus times 1 plus t squared plus b lots of 1 plus t plus ct plus d lots of 1 plus t all squared. All right, I'm going to choose some simple values for t, which will simplify this as much as possible. -1 is quite nice because it gets rid of the a and the c and the d in one go. -4 equals 2b, so b is -2. I've chosen t equals 0. You didn't have to choose 0. You could have chosen alternative values of t, but when t is 0, we get 0 equals a subtract 2 plus d. And then I've chosen t to be 1. 4 is equal to 4a subtract 4 plus 9c plus 4d. And we can solve those simultaneously to deduce that c must be equal to 0. And finally, I've gone for t equals 2. We get 8 equals 15a subtract 10 plus 9d. And solving those, we can get a equals 0, d equals 2. So our original integral that they've asked us to evaluate, 1 over 1 plus cosec x, the integral of that with respect to x is exactly the same as the integral of, well, b is -2 and d is 2, so we'll have d over, which is 2 over 1 plus t squared, subtract b over, that's 2 over 1 plus t all squared dt. The integral of 2 over 1 plus t squared is 2 lots of arctan t, or inverse tan t, and the integral of 2 over 1 plus t all squared is going to be minus 2 over 1 plus t, so the minuses cancel, we get plus 2 over 1 plus t plus k. Then we can reverse the substitution, so we know that t is equal to tan of x over 2. So if we put tan of x over 2 into that, we get 2 lots of x over 2, plus 2 over 1 plus tan of x over 2 plus our constant of integration k. 2 times x over 2 is just x, and we get the answer that they wanted, x plus 2 over 1 plus tan of x over 2 plus k. Okay, question 6. This is asking us to use the rule of Guillaume de L'Hopital, born 1661 to 1704. He's the L'Hopital behind the famous rule for indeterminate limits. That's when you have 0 over 0 or infinity over infinity or something like that. It gives us a little escape hatch we can use to evaluate those. L'Hopital was a French nobleman and mathematician. He was born into a wealthy military family in Paris, originally destined to join the army and become a cavalry officer, but he had poor eyesight, which forced him to give that up, after which he devoted himself to mathematics full time. He was part of the sort of first generation of mathematicians that started learning calculus after its invention by Leibniz and Newton, and it was only understood by a handful of people at that time. L'Hopital had lots of money, and so he hired a younger mathematician than him, Johann Bernoulli, one of the Bernoullis, as a private tutor to teach him the new differential calculus. Bernoulli was younger, brilliant, and not especially wealthy, so that arrangement worked for both of them. It's almost certain that it was Bernoulli who created the technique, but it was L'Hopital who published it first in his book L'analyse des infiniment petites pour l'intelligence de lignes courbées, publié en 1696 par le marquis de L'Hopital et considéré comme le premier véritable manuel de calcul différentiel. Anyway, we've differentiated twice, and we've plugged in 0, and we've got 49 over 18 out, which is reassuring. Part 2, using the theorem of Gottfried Wilhelm Leibniz. He was 1646 to 1716, one of the true giants of mathematics, probably the single most important person. For the notation that I'm using right now, every time you write a dy by dx, you are using the expression of a ratio of tiny changes, which Leibniz was the first to do. There was of course, you probably know this already, having studied maths at this level, the great battle about who invented calculus. Was it Newton? Was it Leibniz? I think the consensus has formed that they both did it, probably at about the same time, perhaps Newton slightly first, but he didn't publish it immediately, even though he got a lot of the credit afterwards. However, Leibniz, he sort of won the language battle. We use his notation today. He did a lot of other things as well, Leibniz, as well as calculus. He formalized the binary counting system, 0, 1, 1, 0, 1, 1, 1, 0, 0, etc. He also designed a mechanical calculator, laid the groundwork for symbolic logic, and sort of developed some systems of reasoning we'd recognize in computer science and algorithms today. So every calculator, computer, and derivative lesson owes something to Leibniz. Anyway, his theorem allows us to use the repeated product rule as many times as we like. When we take our two functions here, we've got an x squared and an e to the 3x. Well, differentiating the x squared twice will get us down to 2, and then it will disappear. So everything else will have a 0 in. So we only need to consider the x squared, the 2x, and the 2 as the 3 different parts. Differentiating e to the 3x, we're going to multiply by 3 each time. And we can generalize that to get the kth derivative of e to the 3x, which will be 3 to the k times by e to the 3x. And that gives me everything we need to use Leibniz's theorem. So the x squared times 3 to the k e to the 3x, and then so on. Then we'll have the k times 2x times 3 to the k minus 1 times e to the 3x, then plus the k times k minus 1 over 2 lots of 2 times 3 to the k minus 2 lots of 3x, which is quite nice because we can factorize out 3 to the power of k minus 2 and 3 e to the 3x, leaving us that lots of 9x squared plus 6kx plus k lots of k minus 1, which is of the form the question wanted. For part B, we can use that to find the ninth derivative being the solutions to the ninth derivative being equal to 0. Well, that happens when k is 9. So we can use our theorem above. Plug k equals 9 into it. We get the 9th differential will be equal to 3 to the power 7 e to the 3x, lots of 9x squared plus 54x plus 72. Well, we want the 9th derivative to be 0, so I shall replace d9y by dx to the 9 with 0. Dividing by 3 to the 7 and e to the 3x immediately to make them disappear. We can find, because they won't be equal to 0, so that's fine. We will get our solutions from 0 being equal to 9x squared plus 54x plus 72. Everything's divisible by 9 there. Factorizes really nicely, and we get our two solutions, x equals -4 or -2. That's question 6. Question 7 is the first order differential equation question. It gives us the transformation it wants us to use, x equals 1 over p squared. So I'm going to start with that, differentiate it with respect to t. So dx by dt will be equal to -2 lots of p to the -3 times by dp by dt. Quick rearrangement of that, we'll get dp by dt equals minus p cubed over 2 lots of dx by dt. Then I can substitute that into the given equation, so replacing dp by dt with minus p cubed over 2 lots of dx by dt. That will be equal to 40 lots of, should be a capital P there, apologies, because I've spotted it, you can't write it in complaint. And then subtract 1 at the end. Then dividing everything by minus p squared and timesing everything by 2, we can get dx by dt will be equal to minus 8t plus 2 over p squared. 2 over p squared is, of course, 2 lots of x. X is 1 over p. And lastly, subtracting the 2x from both sides gives us the differential equation that the question wanted. Okay, on to part B. We now need to solve the differential equation. So we'll start with the dx by dt, subtract 2x equals -8t. To do this, we're going to need to calculate an integrating factor. So e to the power of the integral of -2 dt. That's going to be e to the -2t. That's our integrating factor. We'll multiply both sides by that. Multiply both sides by e to the -2t, giving us e to the -2t lots of dx by dt. Subtract 2x lots of e to the -2t will be equal to -8t times e to the -2t. That's nice because we can reverse the product rule on the left-hand side. So the left-hand side will be the differential of x e to the -2t. That's the power of the integrating factor there. That's going to be equal to -8t e to the -2t. Right, so if we integrate both sides, the left-hand side will get just the x e to the -2t. That will be equal to -8 lots of, I'll take the -8 out the front, -8 lots of the integral of t e to the -2t dt. And we have a standard integration by parts to carry out. Select u to be t, because it differentiates to 1, v dash to be e to the -2t, which we can integrate easily. So we now have xe to the negative 2t will be equal to negative 8 lots of, and then u times v. Subtract the integral of v du dx, whatever way you like to think about integration by parts. I'll take the half out the front for the second integral. And we can calculate and expand all of that out. So we get xe to the minus 2t will be equal to 4t lots of e to the minus 2t plus 2 lots of e to the minus 2t. That's the half divided by the 2 times by the 8 with all the minuses cancelling nicely, plus the constant of integration k. Then timesing everything by e to the 2t, we'll get x equals 4t plus 2 plus ke to the 2t. We know that x is 1 over p squared, so I can flip the right hand side. P squared will be equal to 1 over 4t plus 2 plus ke to the 2t. Then using the values they give us in the question, p equals 0.5 when t equals 0, substituting those in, we'll get a quarter is equal to 1 over 2 plus k. And we can solve that to find that k must be equal to 2. And we have our final solution to the differential equation. So p squared equals 1 over 4t plus 2 plus 2e to the 2t. Part C, well, to test our model, we'll plug in 3 and see what we get out. And I'll plug 3 into our equation, and I'm going to square root it as well. So p will be equal to 1 over, or the square root of 1 over, and then 12 plus 2 is 14 plus 2 e to the 6. Plug that into your calculator, you get 0.0349. This is very close to the 0.034 that they gave us in the question, and that suggests that the model is a pretty accurate one. And that's my conclusion. It is reliable. Question 8, this one's about the ellipse. Some quite hairy algebra in this question. It gives us the equation of the ellipse and gives us a general equation of a straight line, y equals mx plus c. Well, to find conditions for these intersections, we can substitute y equals mx plus y for mx plus c into the equation of our ellipse. I'm going to multiply both sides by 576. That's the lowest common multiple of 64 and 36, just to get rid of all of the fractions there. And I'm going to expand out the mx plus c squared as well. And then one last full expansion, so the 16 across the expanded mx plus c squared. And then lastly, I'll bring the 576 onto the left, and I will factorize, essentially factorize the coefficients of x squared out the front, and write it in descending powers of x. So we'll have 16m squared plus 9 lots of x squared plus 32cm lots of x, and then the constant 16c squared minus 576 equals 0. and therefore we can deduce that k must be negative 576, sorry. Part B, we're told that the line is a tangent to E and that it passes through the point 10, 20. Well, it passing through the point 10, 20 is useful. It allows us to write C in terms of M, so C will be equal to 20 subtract 10m. Now, due to the fact it's a tangent, I had the idea of differentiating the equation for the ellipse and seeing if I could do anything useful with that. I ended up abandoning that idea and just sticking to looking at the discriminant of the quadratic, which would be equal to 0. I'm not convinced that my solution here is the best one, or indeed it's not particularly elegant. It works, but I'd welcome better solutions, of which I'm convinced there will be some out there. So if you have a better one than that, please do write to me. Anyway, here's mine. So b squared minus 4ac, we have b is 32cm, a is of course 16m squared plus 9, and c is 16c squared. Subtract 576, so b squared minus 4ac equals 0. I'm going to start expanding some of that out. Factorizing 16 out of the 16c squared minus 576 as well allows us to divide everything by 64. Dividing by 64 then removes the 64 in front of the second bracket, allowing me to carry out the double bracket expansion. It also simplifies the first part, just giving us 16c squared m squared. And when I expand all that out and collect like terms, the 16c squared m squareds cancel, and we're left with minus 9c squared plus 576m squared plus 324 equals 0. I can then use the substitution I calculated earlier from the straight line, swapping c for 20 minus 10m. And then squaring the 20 minus 10m, taking a factor of 100 out, we get minus 900 lots of 4 minus 4m plus m squared plus 576m squared plus 324 is equal to 0. And that all boils down quite nicely to 9m squared minus 100m plus 91 equals 0. I'm convinced there's easier ways to get to that quadratic, but there you go, there's one path. Factorizes nicely, 9m minus 91, lots of m minus 1 equals 0, giving us two gradients. M is going to be 91 over 9 or 1. You can work out c by doing 20 subtract 10m, giving us two values of c, negative 730 over 9, or anything equivalent to that, or 10. And so the two possible equations of L are going to be y equals 91 over 9 lots of x minus 730 over 9, or equivalent, or y equals x plus 10. There we go. Question 9 begins with a parallelogram in 3D space. Part A would like us to calculate its area, so I'm going to use the shortcut, the formula for finding the area of a parallelogram by finding the modulus of the cross product. I'm going to use the two vectors e to f and e to h. So e to f minus 3 minus 113, e to h is 342. Cross product of that will be negative 1 times 2, subtract 13 times 4, and then 13 times 3, subtract negative 3 times 2, and lastly negative 3 times 4, subtract negative 1 times 3. Comes out as negative 54, 45, and negative 9. And the modulus of that, stick it into Pythagoras. It's going to be 9 lots of the square root of 62. For part B, the equation of the line, so we're going to have r subtract a point crossed with a vector that is perpendicular to the plane. We've actually calculated one of those already in part A. So the point they've given us e, so r subtract 10, negative 6, negative 1. If we cross that with, I've taken the cross product, negative 54, 45, and negative 9, divided it all by negative 9 to give 6, negative 5, 1. But you could have used any multiple of that for part B. For part C, the first thing I'm going to do is find the equation of the opposite face, the face pi. We know that 25 minus 4, 13 lies on the point, so we're going to use ax plus by plus cz equals d version of the equation of the plane. Plug the numbers in, and we get that d must be equal to 183. So pi has equation 6x minus 5y plus z equals 183. Now we're going to try and work out the vector that is orthogonal to the two vectors we've already calculated the cross product for. So I'm going to construct a new vector that takes me from the point E and then does a scalar multiple of 6 minus 5, 1 to take us on to pi. Call that scalar multiple lambda. And then we can solve the equation to deduce that lambda must be equal to 2. So it's 2 lots of our vector 6 minus 5, 1 that takes us from our face P onto our face pi. Then using the formula for calculating the volume of a parallelepiped, A dot B cross C, well, we've already done the modulus of B cross C, so that's 9 root 62, so dot that with A, so that's going to be 2 lots of the vector, the modulus of the vector 6 minus 5, 1, so 9 root 62 times 2 lots of Pythagoras, that 6 squared plus 5 squared plus 1 squared gives me a volume of 1,116 cubic units. Well done if you got that one. All right, great.